All right, so it looks like we're recording, so I'll get started. So today, we have the pleasure to introduce Daochen Wang, who is a relatively new addition to the UBC computer science faculty. And Daochen got his PhD working with Andrew Childs at the University of Maryland, and he's been working on a variety of very interesting topics in quantum algorithms and quantum complexity theory. And today we're going to hear about some of the ideas he's working on and bringing like divide and conquer algorithms to the quantum domain. So thanks, Daochen.
Yeah, thank you. Thank you very much, Drew, for the introduction. Yeah, and thanks everyone for coming to the seminar. So today I'll be talking about some work I did on quantum divide and conquer with some brilliant co-authors. So that's my advisor, Andrew Childs, Robin Kothari, who at the time was a researcher at Microsoft and has since moved to Google Quantum AI. Another student of Andrew's, Matt Kovacs-Deak, and also Aarthi Sundaram. So this work has the, can you see my cursor? I guess maybe not cursor. Yeah, oh, can you see my cursor? Oh.
Yes, it's up there.
Yeah, okay. Yeah, so this has arXiv link as follows, and it was also presented at QIP 2023. Okay, so since I'm relatively new to the area, let me just say a little bit about sort of my research agenda and what I find interesting. So the main motivation, as we know, for building a quantum computer is the promise of quantum speedups. So a quantum speedup, by definition, means when you have a computational problem that can be solved faster on a quantum computer compared to any classical computer. So my research is focused on quantum speedups. And the way I like to think about this is I like to think about it in terms of three components. So structure, design, and application. So we know that quantum computing is not a magic machine that speeds up the solution of every problem. So therefore, a first question is to understand the problem structures which are susceptible to quantum speedups in the first place. So in terms of this analogy I've shown here with a well, understanding structure allows us to understand sort of where the water is underground. Now, once we know where the water is, we then need to sort of design and build the well that enables us to pull the water up. So designing quantum algorithms from scratch is very difficult. Since the principles of quantum mechanics are very non-intuitive. So fortunately, there are several algorithmic design frameworks that are more intuitive to use. So a design framework is like the well in this analogy and allows us to get the water out more easily. And so once you have the setup with the water and the well, the final step is to realize the speedup in a real-world application, which corresponds to pulling up the water in a bucket. So today's talk falls into the design component of my research. And before diving in, I just want to give you some examples of problems that have quantum speedups and how they relate to previously existing frameworks for quantum algorithm design. Okay. So here's some examples of exponential quantum speedups. So the most famous of these is, as we all know, the factoring problem, where you take a natural number and you want to break it up into its prime factors. Maybe less well-known cousin of the factoring algorithm is something known as solving Pell's equation. So this is a number theoretic equation. X squared minus d times y squared is equal to 1, where d is a non-square positive integer, and you want to solve for x and y in the integers. We also have simulating quantum dynamics. So here is the Schrödinger equation, and we want to evolve this equation on a quantum computer, producing a quantum state that encodes the solution psi. Another one is solving linear systems quantumly. So we start with the equation AX is equal to B, and the goal is to output the quantum state that encodes the solution X. Importantly, this really is a sort of a quantum problem. The solution that gets output is not X written on a piece of paper, but rather X encoded in the amplitudes of some quantum states. So that's why I say it's solving linear systems quantumly. Yet another example of an exponential quantum speedup is the so-called exit finding problem in the so-called blue trees graph. So here, what you're given is the ability to query what the neighbors of each vertex is, and your goal is to start from the entrance and end up at the exit vertex. So these are all problems that are known to admit exponential quantum speedups, either relative to an oracle or relative to the best known classical algorithm. There are also examples of polynomial quantum speedups. So the most famous of these is probably unstructured search. So for example, you can consider a satisfiability formula SAT. So you have a variables U1, U2, U3, U4, U5, and you want to see if there's assignment of bits to these variables such that the formula I've shown on the slide evaluates to 1. There's also something called maximum finding. This is a very generic problem. So you have a function f, and you want to find the input x that maximizes f. Another interesting example is Monte Carlo mean estimation. So here you have a random variable x, and you want to estimate what the expectation value of f of x is over the randomness of x. So classically, what you would do is you would take samples distributed according to the random variable x and evaluate f on these samples and perform the sum. I guess there should also be a 1 over n that's missing from the slide. So this is also a procedure that can admit a polynomial, in fact, quadratic quantum speedup. Something that may be less well known to a more general audience is something called element distinctness. So here, the input is a string of numbers, and what you're supposed to output is a bit indicating whether there's two symbols that are the same in the string. So so in this example here, the answer should be not distinct because I see that 8 appears twice. Lastly, there's the triangle detection problem. So here, you're given the ability to query whether edges of a graph exists, or alternatively, the adjacency matrix of a graph. And your goal is to decide whether this graph contains a triangle. In this example on the slide, the answer should be yes, because clearly there's a triangle between vertices 2, 3, and 4. So these are some examples of polynomial quantum speedups. So let's see how these problems fit into existing algorithmic design frameworks. So for factoring and solving Pell's equation, they fall under the heading of quantum Fourier transform. So both of these can be solved using a procedure known as the quantum Fourier transform, 1 over the real over the integers, which corresponds to factoring, and 1 over sort of the reals, which corresponds to Pell's equation. Simulating quantum dynamics and solving linear systems quantumly can fall under the heading of quantum signal processing. This is an understanding that has been developing for the past maybe 5, 6 years, where these problems can be basically reduced using the framework of quantum signal processing to polynomial approximations of different smooth functions. So evolving Schrödinger's equation in this framework essentially corresponds to finding a polynomial approximation to the function e to the minus ixt, and solving linear systems essentially corresponds to finding a polynomial approximation to the function x to the minus 1. Okay, so what about these polynomial speedups? A lot of them fall under the heading Grover search, or you might think of them as falling under a slight generalization of Grover search called amplitude amplification. And there are also some more exotic examples of polynomial speedup, so element distinctness and triangle detection, and these can be solved optimally using a framework called quantum walk, where the design intuition is that you first come up with a classical random walk algorithm for the problem, and then there's some very interesting way of speeding up components of that classical random walk. And the reason why we like these frameworks, as I might have already implied, is that they allow us to more easily design quantum algorithms, often by reducing the design process to some classical problem. For example, either polynomial approximations to smooth functions, or designing a Markov chain, that a classical Markov chain that converges fast to the solution. So our work is motivated by one of the most powerful frameworks for classical algorithm design, so known as divide and conquer. So in divide and conquer, the strategy is highly general, and you start by dividing a problem into its subproblems. You recursively solve each subproblem, and then you combine the solutions of the subproblems to solve the full problem. Okay, so what's an example of this? An example of this is merge sort. So here you have a list of numbers, and you want to sort them in, let's say, increasing order. So how would these steps be applied here? Well, we first break the problem into two parts. So I take the first half, I take the second half. Then for each part, I solve the problem by invoking a sort of a subinstance of the original problem of half the size. And then once I've sorted them, I merge them together in linear time in the length of the input to form the solution, which is a globally sorted list. So how do we analyze the complexity of this? Well, it's pretty easy. So the cost of solving the entire problem of size n is equal to 2 times the cost of solving the problem on input of size n over 2. These strings in the first stage are of size n over 2. And you also need to add on the cost of merging, which is O(n) time problem. And if you look at this recursion, you can use very standard techniques to see that it solves to Cn is equal to the order of log of n times log of n. So one thing to keep in mind here, and for the later parts of the talk, is that the solution to this recurrence is sensitive to the constant multiplying the cost of the subproblem, i.e. This 2 here, this 2, but it is not sensitive to any constant multiplying the cost of the auxiliary problem that's hidden in the big O. So in this big O, the constant factor here might be a billion. It does not impact whether Cn solves to order n times log n or not. On the other hand, if this 2 changed to a number that's 2.1, the solution Cn will not be of this form. It will be n to some other power. So that is an important thing to bear in mind, and it's a sort of important aspect of our framework. Okay. Any questions at this point? Yeah.
Is this only for like grand complexity? This is also like very complexity between the kind of creative problems with the problems?
Yeah, that's a good question. So the question was, what does C mean kind of rigorously here? So C here could be the time complexity of solving the problem. In our framework, we'll be dealing with something less general, known as the query complexity. I'll discuss what that means in later slides. And in fact, one of the open questions of this work is to see if the framework extends to time complexity instead of query complexity. Yes, so I've been sort of deliberately vague about the precise meaning of C here. In this example, C could be the time complexity, but later on, the C will represent something different. Okay. Okay, so we see this classical algorithmic design framework that's very nice, that's very intuitive. And we ask the question, if we really wanted a quantum version of this intuition, a quantum version of divide and conquer, how might we proceed? And the motivating example that we started with was the following problem. So consider a string x of n bits. So say that it's unknown to you what the string is. And the question you want to compute on the string is whether there is a bit of x that is equal to 1. And the answer is denoted as O of x, because the O of x is defined to be x1 or x2 or up to xn, which is precisely the answer to the question. Now, how would you do this classically? Well, we have this divide and conquer recurrence, which is that the OR of x is equal to the OR of 2 bits. It's equal to the OR of the left half of x, denoted x left. And I guess there should be a OR also on the x right. That's a typo. So OR of x can be computed as the OR of 2 bits, one of which is the OR of x left, one of which is the OR of x right. So classically, by the same argument, we have Cn is less than or equal to 2 times Cn over 2, which solves to Cn less than or equal to n. Now, you might hope for the following in a quantum situation. Okay. So because computing the OR of n objects has quantum cost order of square root of n, courtesy of Grover's search, we might hope that for the quantum version of this recurrence, because we are searching over sort of 2 bits, the OR of x left and the OR of x right, we might hope that the 2 in the coefficient of Cn over 2 gets turned into a square root of 2. And actually, if it really did turn into a square root of 2, this recurrence relation solves to C of n is less than or equal to order square root of n, which is the right answer, in fact, for this question. But this is not really justified. So for 3 reasons, at least. So the quantum query complexity of OR is only up to order square root of n. It's not exactly square root of n. And as I mentioned, any constant changes to the coefficient here really affects what the solution to the recurrence is. The second reason is that Grover's algorithm has bounded error, i.e. it does not work perfectly, unlike the classical situation. And this recurrence does not address the need for error reduction. And a final point is that square root of 2 is not even an integer. So, and as we'll see later, these numbers, Cn and Cn over 2 are integers. So like this equation doesn't even make sense in a way. Nevertheless, we will show that in this example and many others, something like this can be done in a rigorous way. So the main message of our work is that for certain problems, there's a rigorous way to derive the intuitive quantum recurrence, like in the previous slide. So, so if classically you can divide a problem of size n into A instances of size n over B each, a typical classical divide and conquer recurrence might look like this. It's sort of a slightly generalized form of what we have already seen. And the message of this work is that in many such situations, the classical recurrence can be turned into a quantum recurrence that looks something like what's shown on the slide, where the A has now been square rooted. And the C arcs of n, which corresponds to the cost of solving an auxiliary problem, has got an additional subscript of Q, which just denotes that it's the quantum cost of solving the auxiliary problem. So going back to the sort of the question earlier, we need to be a bit more careful about what we mean by these C's. And to be rigorous, let me talk to you a little bit about query complexity. So the query complexity model is a simplified model of computation where you're given a function f, and you want to decide how many queries to the oracle encoding an input x in the domain of f does the algorithm A need to make in order to compute f of x correctly with probability at least 2/3 for all x in that E should be sigma n. So the answer to this question is denoted D of f, R of f, and Q of f when A is deterministic, randomized, and quantum respectively. And within this model, we say that computing the function f admits a quantum speedup if and only if Q of f is strictly less than R of f. So R of f is, in this model, what is representing the most powerful type of classical algorithm, which can also use randomness. So here, a classical query is something where you feed in an index I, and the output is the value of xi. So the i's symbol of the input x. In the quantum case, a quantum query is described by a unitary matrix whose behavior on the standard basis states ket I, ket A is defined as shown. So the quantum oracle definition is motivated by the fact that whenever the mapping from I to xi can be computed by a classical circuit, the quantum oracle or the quantum unitary can be computed by a quantum circuit of essentially the same size. So as an example, we can consider f being the OR function, mapping from n bits to 1 bit, and it is well known that R of f is equal to theta of n, because essentially, if you don't read roughly all n of the bits, it could still be that the last bit is 1 or 0, in which case you don't know what the value of all of the input is. On the other hand, Q of f is equal to theta of square root of n, courtesy of Kovacs-Deak. So note that in this model, we do not care about the complexity of any non-query part of the algorithm. We just count the number of calls to the queries, to the oracle. And to arrive at a quantum version of divide and conquer, we employ the so-called adversary quantity. This is a quantity that allows us to precisely control the coefficients that I said was so sensitive, that was so influential to the solution of the recurrence. So for any function, the adversary quantity is a real number that's defined as shown on this slide. So I would say that the precise details of the mathematical definition that's shown here don't matter so much as the observation that it's an object with a very clean mathematical definition. So, so you see a bunch of norms. These things happen to be the spectral norms of matrices, and yeah, so this definition is very nice and clean. There's nothing, mysterious or quantum about it. But the very interesting point about the adversary quantity associated with f is a deep theorem from maybe a decade ago, which showed that the quantum query complexity of any function f is up to constants the same as the adversary quantity of f. In addition, there are more things that are true for the adversary quantity that's not known to be true, in fact, false, for the quantum query complexity. And these are so-called composition theorems. And so the composition theorems allow us to determine the adversary quantity of a function that is composed of subfunctions. So for example, if you have a function g that's defined to be essentially f of 1 and f of 2, then the adversary quantity of this function g squared is at most the adversary quantity of f1 squared plus adversary quantity of f2 squared, and these LMRS authors are the same as the LMRS in the theorem statement. Analogously, you can also prove that for all, there's the same expression. Interestingly, there's also a composition for what I would call the switch case function. So what is this function? So here h of x is equal to g of f of x of x. Okay, so the interpretation of this is to compute h of x, you first want to compute f of x, which switches to a g with a certain subscript, then that you want to evaluate. Okay, so in this type of composition, the adversary quantity of h is less than or equal to 2 times the adversary quantity of f plus the max over all of the possible g's of the adversary quantity of g of s. And this is something that we established in our work.
You have multiple g's
Yeah.
by the domain of f. And
By the codomain of, labeled by the codomain of f, right? And yeah, this is a bit of a sloppy notation. So the max over s here should be, I guess, over the codomain of f. Yeah, good question. Okay, so with these two theorems, what we can have are two strategies for quantum divide and conquer. So the first strategy is, suppose that f is computed as an and/or formula of fi's and an auxiliary f, fox, then if you just combined the composition theorems for and or, you will see that the ADV of f squared is at most the ADV of f ox squared plus the sum of the ADV of the fi squared. And in the switch case situation, we can sort of just port that theorem we saw in the previous slide as is, and we find the following expression. ADV of f is less than or equal to 2 times ADV of f ox plus the max over s of ADV of gs. I will do a trick here where I use the theorem to replace all of the ADV f oxes by the quantum query complexity of f ox, because as the first theorem on the last slide showed, these things are essentially the same up to a constant factor. And for the auxiliary problem, like in the examples we have seen, we do not care about what the constant in this big O is. So this is really fine. So these resulting inequalities, these two resulting inequalities on this slide, can be used to derive divide and conquer recurrences in the quantum setting that sometimes lead to quantum speedup. So another feature of these inequalities is that they mix the adversary quantity and the quantum query complexity. So I see both ADV and Q in these inequalities. So using the adversary quantity is what allows us to tightly control the coefficient in front of the complexity of a subproblem, which is critical for the recurrence to yield something something that has a quantum speedup. But we simply bounded the adversary quantity of the auxiliary problem by its quantum query complexity, because in applications, bounding this is easier to think about than bounding the ADV of f ox. And so these two inequalities are what we'll be using as our workhorses to solve some specific problems. So what are those specific problems that we consider in this work. Okay, so we apply it in this work to 4 string problems. So in my presentation today, I will go over in some detail the application to longest common subsequence and to recognizing regular languages. If you want the details of the other 2 applications, I encourage you to look at our paper. I should say that the first 2 applications shown on the slide, they give simpler analysis of previous work by the authors shown. And also the bounds we obtain are slightly tighter, whereas the last 2 applications are new to this work. I should say that these are proofs of principle that our framework can lead to new and interesting speedups. But just like classical divide and conquer has a multitude of applications, we also expect that our framework would have a multitude of applications that fall outside of this small list discussed in our work. Okay, so let's look at one of these applications first. Let's start with recognizing regular languages. So we will not consider the general setting of recognizing an arbitrary regular language. We will consider, for this talk, recognizing a particular regular language, which basically captures the essential details of how this thing would work in the general case. And so here, we consider sigma being the set 0, 1, 2. And the function we want to compute is defined by the regular expression shown on the slide. Okay, so I know that maybe some of you haven't got a theoretical computer science background. So what does this mean? So the meaning is very simple. So it just means that the function on input of the form on the left should output 1, whereas if it's of the form on the right, it should output no. So what is the form on the left? The form on the left is basically that the string contains a substring that's of the form 2 followed by a bunch of zeros followed by another 2. So on the left, I see 2, 0, 0, 2. So the answer should be 1, or in this more colorful notation, a tick. Whereas for the input on the right, I don't see anything that's of the form 2 followed by a bunch of zeros followed by a 2. So the answer should be no. Does the definition of this function make sense? Okay.
What's an example of like an application which would have similar structure to this? Is this tutorial model to be like that?
Yeah, so interestingly, this is kind of a paradigmatic example of all of the regular languages. So sort of the kind of to recognize an arbitrary regular language, the ideas in the proof of the complexity for this problem can be translated without too much extra effort, regardless of what the regular language is. So this, the details of this are actually worked out not in our paper, but worked out in the paper cited earlier by Aronson, Grier, and Schaefer. Yeah, so in fact, I don't think I'll be able to precisely describe the details here, but I will refer you to that paper to see why this is such a paradigmatic example of a regular language. Yeah, it's a good question. Okay. So what is the strategy to solving this by divide and conquer? Well, if we just think classically, the strategy is obvious. So the 2002, it could either be in the left half of the string, or it could be in the right half of the string. But there's also a third case where it's the zeros of this 2, 0 star 2, 2 followed by a bunch of zeros, 2, straddle the midpoint of the string. And so this notation of Gn is precisely defining the function that is trying to compute whether this last case occurs or not. Then we see that Fn of x is equal to Fn over 2 of x left, or Fn over 2 of x right, or this Gn of x, which just describes the last case I mentioned. So if we let A of n be equal to the ABV of F of n, then by the composition, the and/or composition we saw, or by the first strategy for and/or formulas that we saw, we see that A of n squared is less than or equal to 2 times A of n over 2 squared plus the quantum query complexity of computing this Gn. So it is sort of easy to see that the quantum query complexity of computing this Gn is order square root of n. It's essentially a riff on Grover search. So the whole recurrence solves to A of n is equal to order square root n log n. But now A of n is up to theta notation, the same as Q of Fn. We automatically deduce that the quantum query complexity of the original function f of n is also order square root n log n. Okay, so this is the for the warm-up example for our framework. They already give something that's sort of quite interesting. If you started from scratch and thought about this problem just bare hands using Grover search, it's actually not so straightforward how you would solve this problem using complexity order square root of n up to some log factors. Now let's look at a more involved example of quantum divide and conquer. So here, let's consider the longest common subsequence problem, or rather we will consider a decisional variant of it, known as K common subsequence, or KCS. So in this problem, which is parameterized by a constant K, you're given 2 strings, x and y, and your objective is to decide whether x and y share a subsequence of length k. So a subsequence of a string is a string formed by taking a subset of the positions of the original string. So it's important to note that the subset of positions does not have to be consecutive, but the ordering of the positions must not change. So for example, if we look at the 2 strings Einstein and entwined, the longest common subsequence of these strings is En Tn. So if k were equal to 3, the answer should be yes, they do share a subsequence of length 3. If k is 4, answer is yes. If k is equal to 5, the answer should be no. So what's known about this problem? So it's known that the randomized query complexity of KCS is equal to theta of n for any constant k that's greater than or equal to 1. It's known that if k is equal to 1, the quantum query complexity of this problem is theta n to the 2/3. In fact, if you recall what the element distinctness problem was from earlier, this is a variant of that problem. So and the complexity was established by these folks, Aronson, Shi, and Linus. So in fact, by using a variant of the algorithm used to establish the upper bound for 1CS, you can pretty easily establish that Q of KCS is order n to the 2k over k 2k plus 1. So using the same algorithm as in unbinus 03. The question we ask is, can we do better than this? So the last expression, that's big O notation, it's not known before our work whether it was tight, and the answer, as we'll see, is actually no, it's not tight. You get a better upper bound. So how do we perform the analysis? So we will be dissecting the problem into 2 types of subsequences that share k symbols. And the theorem we will prove is that if ak of n is equal to the adversarial quantity of kcs on input of length n, then ak of n is order n to the 2/3 log to the power of k minus 1 times n. Oh, it's not times n, it's just log n to the power of k minus 1. And of course, this is also the bound for the quantum query complexity. So we're doing divide and conquer, so let's divide the input strings x and y into n parts each. Then a KCS can either be what is called simple or composite. So a simple KCS is a KCS where the k colliding symbols are from each from a single part of x and a single part of y. So in this diagram, you see an example of a 2CS in the case m is equal to 3. So we split the problem into 3 parts, and we see that there's a there's a subsequence of x and y of length 2 that collide, which is denoted by this green dumbbell shape. And a composite KCS is any KCS that is not simple. So it's formed by collisions between symbols that come from different parts of x and y. So we can first think about how might we go about detecting a composite KCS. So the observation here is that detecting composite KCS can be done by detecting ICS for I strictly less than k. So if you think about how might a composite KCS be arranged, one of the possibilities is what's shown on the slide. So this means that there's a symbol in the first part of y that collides with a symbol in the second part of x, and there's 3 symbols in the second part of x which collides with 3 symbols in the third part of x, y, and so on. But the point is that to detect each of these lines here, you only need to solve the ICS problem for I strictly less than k, which is why the cost of this sum goes from j is equal to 1 to k minus 1. And just to preview the later strategy is we're just going to do induction on k. So sort of we already in some sense know what the complexity of AJN is. The log n is responsible for some tricks about needing to do binary search in order to detect this specific pattern, because what you need to do is, I guess what I'm showing on this, trying to find on the screen. It's not going to show up on the Zoom, but anyway, this log n is not so important, but it's sort of like some extra processing that you need to do to make this work. Okay, so this is the cost of detecting the composite KCS. Now things that are not composite are simple, so we also need a procedure to detect these simple KCSs. And here, the crucial observation is that we only need to detect if there exists a simple KCS between at most 2 n-1 pairs of length n over m substrings. So n is the number of parts we've divided the problem into, remember? So let's look at this schematically. So recall that simple KCSs are those that go entirely between a single part of x and a single part of y. Since we have divided x into n parts and y also into n parts, there are m squared pairs of parts between x and y. Okay, so a priori, we might expect that we need to solve m squared instances of the KCS problem. But the observation is that we only need to solve a linear in m number of instances of KCS. More precisely, 2n-1 instances of KCS. So let's see why. So suppose we first draw lines between parts that share a common symbol. So the cost of computing whether a line exists between a single pair of parts is order n to the 2/3 using Ambines's algorithm for element distinctness. Therefore, the cost of drawing all m squared of these lines is m squared times order n to the 2/3, which is order n to the 2/3 because m will, as we'll see later, be said to be a constant. Now, say we find that the configuration of lines is as shown in this figure. So now in this figure, there's 1, 2, 3, 4, 5 lines. So there are 5 pairs of parts that share one common symbol. So in this case, we need to solve 5 instances of KCS, where each instance corresponds to each line. Note that if there does not exist a line between 2 parts, it obviously means that they don't even share one symbol, so they obviously cannot share K symbols. So I now claim that this is in fact the worst case scenario. So to see this, suppose there's another line between the third part of X and the third part of Y. In this case, we don't actually need to solve the KCS problem between these parts, because if a KCS did exist between them, it can be combined with the vertical line all the way on the left here to form a composite KCS, which we should have already detected by our previous analysis. More generally, any additional red line between these parts would only make our lives easier. So therefore, the configuration of the black lines is the worst case. So a more formal proof follows by the observation that the configuration of black lines consists of lines of every possible slope. And the maximum number of slopes in the setup is 2n-1. So the slope is like the gradient of these lines. And so this analysis leads to a cost using our divide and conquer framework of the following. So it's order n to the 2/3, which comes from this cost of computing the lines, plus square root 2n-1 times ak of n over m. So the reason that there's a square root on the 2n-1 is because we are computing an OR of 2n-1 KCS subproblems. The plus sign is a consequence of the adversary composition for a switch case, or alternatively, you can think of it as a consequence of our second strategy. Okay, so let's just put everything together. We have that the cost of detecting a composite KCS costs what's shown, and the cost of detecting a simple KCS as what's shown. So if we induct on the theorem on K, we see that AK of n is less than or equal to square root 2n-1 times AK n over m plus order n to the 2/3 log n to the power of k-1. So yeah, if you plug AKN, the expression for AKN into this expression, I guess J only goes up to k-1. So the power in here will be log of k-1 times another log. So it'll be log k-1. That's why it's still k-1 power here. And now this is a recurrence that we can look at any textbook to see that it solves to AKN is order n to the 2/3 log n to the k-1, provided the log base n of square root 2n-1 is strictly less than 2/3. And this is satisfied as soon as we take n is greater than or equal to 7. So what this means is that if we split the problem into at least 7 parts, then a quantum divide and conquer strategy will allow us to obtain a final complexity of order essentially n to the 2/3. And in fact, this is an optimal query complexity for this problem. So in conclusion, this work has introduced a framework for designing quantum query algorithms using classical divide and conquer intuition. We've discussed applications to regular languages and string rotation, I guess not string rotation, to regular languages with tighter bounds. something else we haven't discussed is that it gives a quantum algorithm for KIS increasing subsequence using order square root n queries, which is actually also optimal. And the one we did discuss is a quantum algorithm for KCS using order n to the 2/3 queries, which is also optimal. So some open questions. The first is, can we find other applications of this framework? In particular, can we find applications where the combining operations are not and or the switch case? So a second question is, can we obtain super quadratic speedups using this framework? So that's a trivial way in which you can sort of come up with super quadratic speedups in this framework, because you can just sort of embed your super polynomial quantum speedup into the computation of the auxiliary function. But what we sort of want is a sort of a more synergistic way of coming up with a super polynomial speedup using this framework. And finally, is the question about time complexity. So everything I've said in terms of complexity has been implicitly, I suppose I did have a slide on query complexity, so semi-explicitly been referring to query complexity, but it would be very interesting to see how this framework generalizes if we want to actually think about time complexity, which is the complexity that corresponds to our real-world intuition of how long it takes a problem to be solved. And on this front, there's been some nice follow-up works by these authors very recently that partly resolve this question. And so with that, I'd like to finish my talk, and I'd be happy to take any questions. So thank you very much.
All right, great. Thanks, Daochen. So if there are any questions, please either type them in the chat or feel free to unmute yourself and ask.